And we are live, and I am RJ Shine, and I'm joined by Jason, Awake Souls. How you doing, bro? I can't hear anything on my end. I got to do some stuff, so take it away.
All right, yeah, I can hear you, and I think we're live. So we are in the process of doing some upgrades with some of our tech, new computer, new cameras, different things, and so this is our first run with some new equipment. And we're having a few issues. It's a little bit of a headbanger today trying to get this all set up. So please bear with us, but eventually we'll get all the bugs worked out and we should have some higher quality stuff going forward. That was the plan. We'll see how that works out. But yeah, thanks for joining everybody while Ronnie is getting the audio tuned up. Shout out to Yahawashai's daughter, Town Center, PJCnet showed up. So small group tonight. We're on Beyond Flat Earth. It's because the Awake Souls channel's got 2 community guideline strikes right now. And so it's going to be a smaller audience, but yeah, tonight we're going to be doing some, we call it free energy. All right. So there's truly no free energy where it costs you nothing, but there are free energies where you get the fuel for free. So you still need to have the device to collect it, but the actual fuel is given to us by nature for free, and it's easily accessible for everybody in a couple of different ways. So you can be picking it up through solar, you can be picking it up through wind, you can be picking it up through hydropower, but we're going to be showing you some new breakthroughs in technology where they're dripping out. So they're talking about the hydrogen economy coming up as opposed to the petro economy that we're on right now. And the hydro is hydrogen, and they're actually have had this technology for a long time. So I've been doing the research and found out that hydrogen was first discovered by Robert Boyle. And so this was a long time ago, and there's some interesting tidbits. The very first combustion engine, right, that ever was made, guess what it ran on, everybody? Guess what it ran on? Hydrogen. First combustion engine, internal combustion engine, ran on hydrogen. It's funny that we would be going back to that now, considering it was the first fuel used. But yeah, there's so many lies, so many deceptions. Just let me know when you've got things tuned up, brother.
I mean, I can hear you, so we're good. I can't hear anything else. I can't hear if there's background music playing. I've turned it off. We're just going to have to go with it. Hopefully I can hear your screen share sound. It had something to do with Zoom. Zoom is acting very odd. It's crazy what they do with these other tools that we must use.
I know Zoom is the problem. Part of the tech thing that we're doing right now is trying to figure out how we can get both of us together without Zoom, right? Because it's crap. It's crap.
Yeah,
I know that
they're throttling, like your camera's being throttled right now, right? It's blurry. You've got a brand new, what is it, iPhone 13?
14, yeah.
14. You got the lights going. You should be as clear, if not clearer than me. Better. You have a clear. Can you hear me? Yeah, you should be able to hear me now. But for some reason, their bandwidth is being jacked. We have to come up with our completely different way to stream. When we do our streams together, the two of us, we're going to have to come up with a broadcast studio system where we connect the 2 computers somehow, and we have the same abilities, because your voice is muffled when you talk through Zoom, and your camera is also being throttled, and we can't have it. We want to have clear everything to be the way that we want it, and we're going to continue to push forward. And tonight's just basically you're going to be going through some new free energy type technology. And when we say free energy, like you had said before, the free part comes from the sun, the wind, the tide, and reactions of different things that we can collect throughout the realm. There's nothing free. You actually have to spend money to create it. It's not free. You have to buy the materials. You have to learn how to store it, how to use them. So what I'm interested, so you brought up Boyle. Boyle was a character that you said was back in the 1500s, possibly?
No, I would have to look that up. I think it was later than that.
So he was the first one to create a reaction where he ended up capturing hydrogen, right?
Yeah. And guess how he captured it?
Well, tell me.
Um, he he f- he first produced hydrogen by mixing aluminum and an acid. Is a sulfuric something, and we'll come across it at some point. But he did not use electrolysis to get his hydrogen. He did it through a chemical reaction of aluminum and an acid, like sulfuric acid or something like that. So that's how hydrogen was discovered, is through the chemicals, not through the electrolysis. But yeah, there's a whole bunch of other ways that you can get hydrogen out of stuff. Use a different metal and then a different acid, boom, hydrogen. Use There's so many combinations. So as we go through this information, people are going to start to see that what we're really interested in is the hydrogen and how we can get it the most efficient way, and how we can store it the most efficient way, and then how are we going to put it to use. So there's so many things that we can do with it once we've got some of it produced, isolated, and stored, right?
Yeah, so I'm remembering correctly from our was it lunch break talk. It was stainless steel shavings put into an electrolyzer with tubes leaving the tops of the bottles. Two bottles, two steel shavings in each bottle, and then the electrolyzer would create the positive and the negative, and that's what he found the reaction to be. Correct?
What? uh, I thought you said
Again,
something about an electrolyzer.
yeah, boil. What he did was he took stainless steel shavings and he put them
No,
in in a
no,
bottle. What?
no, no. I just explained that he used chemicals. He used aluminum and like sulfuric acid.
Oh,
No,
I'm
no, like,
confusing a different experiment.
yeah, yeah. No, it was he did not produce hydrogen through electrolysis. He did it through a chemical reaction with aluminum and sulfuric acid. Yeah,
Now I remember correctly. It was the other experiment where he used the electrolyzer, not boil.
yeah. Yeah, that came along much later, I think. So there's ways of getting hydrogen without producing electricity first, everybody. We could recycle our aluminum cans by throwing it into an acid, and guess what? It creates hydrogen. So that hydrogen can then be used in fuel cells, and that can drive electric motors. You're going to see that energy is it's constant. You can transform it from one thing to another, and it's really balanced. We have so many options as far as what state we want something to be in, because it's lightest, it's the easiest to transport, it's the most condensed, and in what states things have the most thermal energy. So megajoules and stuff like this are measurements that we'll eventually become accustomed to, and it'll mean something, just like, when somebody tells you it's 80 degrees Fahrenheit, and then somebody tells you that it's 50 megajoules per kilogram, you're like, okay, I get that, because you have something to relate it to. It'll just take some time. This is a new topic, but energy it's such an important thing, really. Like, we didn't have electricity, if we didn't have motor vehicles and these types of things, life would be a whole lot different,
Yeah, totally.
150 years ago, right?
Yeah, yeah. Well, again, the interesting thing is you said that we can create hydrogen without having to use electricity. So that's something that should be looked into with chemical reactions. That's something that we want to do. And then also looking at the other ways. So you're going to be going through a whole wide range of different free energy type topics tonight that we're going to walk through, right?
Yeah, so there's a few things now that I'm paying attention in this. Everybody knows how astroturfing works. um they start directing headlines to a person based on what they're interested into. So now that I've really focused some energy into free energy. Now all of a sudden I'm getting all these headlines and articles, and a lot of this stuff is breaking new and recent. We've got articles from like a month ago, stuff within the last year that are big things that I've never even heard of or contemplated before, as far as storage mechanisms, ways that we would be able to produce hydrogen more efficiently, stuff like this. So they're dripping it out. This is part of their plan. They intend to shift to a hydrogen economy. They've kept all this stuff hidden from us. Like, we've got people in the chat that don't understand that, yeah, electric cars, that was the thing back in the 1900s. Right? We totally regressed.
Yeah, early 1900s, and they only had motors in one of the wheels that powered the whole car, right? And they were able to swap out the batteries at the gas station. Right? And they didn't catch on fire when they got wet.
Yeah, so that's one of the new breakthrough technologies is now they're actually talking about solid state batteries, right? They've probably had them the entire time, but instead of having the typical lithium ion with the acid and stuff, where this, it catches on fire, we're hearing about the problems with that. And so these solid state batteries have none of those problems. Plus more energy storage. Right?
Yeah, totally. So do you want to transfer over into the screen share, and we get into some of these tabs? Now, I don't understand why I can't hear anything, but I can hear you, so that's all that matters. And I'm hoping that I'm going to be able to hear the audio and the video. So I'm going to get ready to do the screen share, everybody. Thanks for tuning in. Sorry about the glitches. Like Jason said, we're trying to upgrade everything, and it's going to take a little bit of work. We're trying to get it prepared for the new year that's coming, for 2023. We want to have upgraded everything. So bear with us. Not quite yet. Give me one second. Now you're able to. Thank you, everybody, for tuning in. While Jason gets set up, I'll just continue to talk here. Hey, Adam. Hey, Joe. Hey, Town Center. Hey, PJ CNET. Hey, last but absolutely not least, hey, YD. Thank you for tuning in. You're going to get some new free energy type stuff. So I'm going to put your screen on now, and we'll get ready to go. And you're ready to talk. I'll mute and get set up, too.
All right. So we've got a couple videos, a couple articles, and right. So this first one is energy storage, and this was something that we talked about a while ago when we were doing the hydrogen is fuel, water is fuel, the jet fuel hoax, all that kind of stuff. I mean, that was a number of years ago already, but we were talking about flywheels, and I've got a flywheel out here that we're going to show you how flywheels can be used as energy storage mechanisms. There's so many different ways. So this is going to be one of the energy storage mechanisms, and we've got a couple more, and then some breakthroughs in hydrogen that you might not have heard about yet. So this article or video is The Mechanical Battery Explained, a Flywheel Comeback. This is Undecided with Matt Farrell, a verified YouTuber with 1.09 million subs. He's got 2.3 million views on this from a year ago. And so it's not like this is hidden secret stuff, but why aren't we using it is going to be the question, everybody. So check out what we can find out about the flywheel.
Is usually lithium-ion batteries. But what if we went old school? Like just spinning things really fast and capturing that kinetic energy kind of old school. I thought I'd explain an example of a mechanical battery, the flywheel. And are they making a comeback? I'm Matt Farrell. Welcome to Undecided. The versatility and dropping costs of lithium-ion batteries have made them a popular option for not only consumer electronics, but also grid-scale energy storage. But it's not the only solution that's out there. The often overlooked technology of flywheels has been reinvented and may be a good fit for supporting renewable energy like solar and wind.
Look at that beautiful thing. That is a piece of metal right there.
Has been reinvented and may be a good fit for supporting renewable energy like solar and wind. High power density, long lifetime, high efficiency, and being carbon free has boosted interest in flywheel technology. But how do flywheels stack up over other energy storage technologies? The world has been shifting from fossil fuels to renewable energy sources in order to achieve low carbon emissions and maintain cheap prices. Both electricity consumption and renewable energy generation have been increasing all over the world in the past few years. In 2018, global energy consumption reached almost 25,000 terawatt hours, and of that, solar and wind only accounted for about 1,827 terawatt hours, or about 5% of the total power generation in the world. Since renewables like solar and wind aren't available 24/7 and can't be turned on and off at any time, energy storage systems need to be placed together with solar and wind farms to make them more widely viable. But why do chemical battery installations get all of the buzz right now? Why not flywheels? I mean, the first question to ask is probably, flywheels? Really? Or maybe actually it's, what are flywheels?
Right? So it's really fallen out of people's knowledge that flywheels were used as an energy storage mechanism in the past. So he's going to go in and talk about the pros and cons of the flywheels, and we need to know the facts about these things.
A flywheel contains a dual-function electric motor to store and generate energy. It operates like an electric motor in an EV to speed up the flywheel using electricity, so that kinetic energy is stored in the spinning wheel. Then when it's turned off, the dual-function electric motor operates like a generator, and the mechanical energy stored in the rotating mass spins the generator's rotor, producing electricity. It's similar to how regen braking works in an EV, but
it also is similar to, you remember those cars where you used to push it, vroom, 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 you get it humming as much as you can, and then you'd slap the button, and then that car would take off.
How could you forget about those?
Yeah.
Right?
So if a vehicle's moving and you're braking, you can use that braking energy to spin up a flywheel so that when you go to take off again, you use that energy for your acceleration, right?
when it comes down to it, a flywheel can be considered a big mechanical battery. To get a little nerdy for a second and talk about physics, the rotational energy of a rotating mass is directly proportional to the moment of inertia, or rotational mass, and angular velocity. That's a lot. For example, imagine that you spin two car wheels of the same mass, one at 30 kilometers an hour and another at 100 kilometers per hour. Which one will be harder to break? You probably guessed the faster one. That's an example of angular velocity at work. Now let's say one of the wheels is 5 kilograms and the other is 10 kilograms. You speed them both up to the exact same velocity, so they're both spinning at 30 kilometers per hour. Which one will be harder to stop this time? If you guessed the heavier one, you got it. And that's an example of rotational mass at work. Optimizing the shape and increasing the rotational speed will boost the energy that's stored in a flywheel. However, speeding up the flywheel increases centrifugal forces it's subjected to, and the resistance of the material that it's made from limits the amount of energy a flywheel can store.
So that's an important point to get. Once you get to a certain mass, a certain diameter, and a certain rotational speed, every material that you can make something out of will get to a certain point where it'll explode and come apart. Right?
Just detonate, gone, pieces.
You can only store so much energy in a mass based on the type of material, right? So, but you can get a lot of energy into it. We're going to get some ideas of how much you can store coming up.
The bottom line is, spinning a flywheel too fast can completely break it apart. Now that's obviously something you want to avoid, but as I mentioned earlier, this is something we've been trying to master for a long time. Flywheels were first used in potter wheels and spindles in ancient Mesopotamia to produce threads. Later they played an important role in the Industrial Revolution, when flywheels were used in engines and machines to smooth out the power delivered by the driving device. However, the first flywheel used exclusively for energy storage was built by John A. Howell in 1883 for a military application. In this case, the flywheel...
See, this, everybody, there's so much bogus stuff. They're going to say that the first time a flywheel was used was for a torpedo. And PSYOP, then the next thing they'll say is that it was used on the space shuttle, or it was, something like that. So flywheels are real, but these ideas that they say that they're being used in the ISS and torpedoes and stuff like that, make believe.
Wheel was installed in a Howell Mark I torpedo and worked as a propulsion.
It's nonsense, right? Yeah.
What's that?
It's nonsense. Why they're bringing torpedoes into this? I'm sorry to interrupt, but this is nonsense. They're going to say that the torpedo was powered by what? A flywheel?
Flywheel.
Okay,
Yeah, you spin it up like we were saying with the push car. You just spin up that flywheel, and then
you could make a mini one of these and show me a demonstration of how it would, make it through the water. But it's definitely not going to detonate and blow up. Yeah. Well, I mean, they saying that it does, right?
yeah, but how would it steer back in those days?
A rudder
in the right direction?
No, there'd have to be a rudder behind the prop at the back of this thing.
Somebody would have to be sitting on it, steering it.
I mean, there's got to be, there's no way to steer it. I know it's so ridiculous. I'm sorry. I can't believe this stupid torpedoes made it into the podcast.
I know, but
I'm sorry.
That's what we run into on all of these topics. They psyoped it all.
Yeah, they have to. We were learning about a great technology, and they throw torpedoes in. Like what? Okay, I'm sorry.
Directional balance. In the 1940s, the concept of flywheels was used.
So here's the bus that PJCnet was talking about.
1940s.
Swiss company Oerlikon, when it released its carbon-free bus containing a flywheel for energy storage.
Carbon-free bus. So they were just using a flywheel here to power this bus.
The gyrobus used energy from the grid to spin up a flywheel system, which operated as a generator while it was on the move.
Oh no, it's got electric, but the storage mechanism for the electricity was the flywheel. That's how they were storing the energy.
When the flywheel is completely charged at about 3,000 RPM, the bus could run for about 6 kilometers at speeds up to 50 to 60 kilometers per hour. Since then, several improvements have been made to flywheels in order to increase power storage capacity with safe operation. Flywheel energy storage systems, or FESS, are essentially composed of a few key components besides the flywheel and electric motor. It includes bearings, an enclosure, and a power electronic converter. FESS have bearings to support the rotor and resist against forces to maintain its position, which allows it to spin at the high velocities, but there's a downside there. Mechanical bearings require high-performance lubricants and frequent maintenance to operate properly, and they're also sensitive to friction that it generates. And that's one of the main losses for flywheels is the friction. To solve for that, expensive magnetic bearings are employed in flywheels that operate at high speeds in order to reduce maintenance basically to zero, since they don't require any lubrication at all. It also helps to increase efficiency due to their minimal losses. Flywheel energy storage systems fall into two categories: low speed and high speed. Low speed flywheels are made up of steel and spin at rates up to 10,000 RPM. These are heavy and use the advantage of their angular mass to increase their stored energy, much like I talked about before. Now, on the other hand, modern flywheels that feature high power density and efficiency can reach up to 100,000 RPM, which makes it store more energy since the flywheel energy is proportional to the square of angular velocity.
Do
we need to have Reds on to explain this, like in layman's terms?
The square. That's if you're trying to produce energy, you always want to hear that there's a square formula, because it doubles anything. So the energy is doubled if you increase the radius, or diameter of the wheel, right? And it's also doubled if you increase the mass of it. So it's like your bonus factor, right, that you get by making the wheel bigger. So one of the things that a lot of people run into in prototyping these things is you try to do it at a small scale that's efficient, where if it doesn't work, you haven't invested too much money. But a lot of this stuff needs to have a certain scale in order to work. So with flywheels, the bigger you can make it and the heavier you can make it, the better.
You still with me? Because I'm not sure I am. Advanced flywheels are housed in a vacuum enclosure to reduce aerodynamic drag. They also have air or magnetic suspension bearing technology to reach those high speeds, and are made of materials with high strength to weight ratios like carbon and fiberglass. In practice, flywheels have fast response to frequency changes, making it a good solution to stabilize grid frequency when unstable variations occur.
All right, so we're talking about some of the pros of flywheels here, and that is if the power goes out and you need to switch over to a storage backup, flywheels, because it's already spun up, it's got the energy stored, it's instantly ready to go. All right, you there? Mm-hmm.
In addition to that, they can be completely charged within a few milliseconds and have considerably longer lifetimes of about 20 years compared to other technologies.
All right. Well, they say 20 years, but if you're going to compare a flywheel to a battery, right? Like a lithium ion battery, everybody can understand that a big chunk of metal or plastic or whatever it's made out of, that's going to last, right? It's going to be around for the next 100 years, 200 years, 400 years. The only thing that you're going to need to replace on this is stuff like bearings. The mass itself, that's not going anywhere. It's never changing. It's never going to degrade. Right?
Yeah, totally. I think the audio glitched out on us again. But so what you're stating is that when you create one of these flywheels, you can encase it in something. It's basically a spinning steel plate, right?
Mm-hmm.
And it's not going to break down. If you have it in a vacuum chamber and it's not exposed to the atmosphere, it's not even going to corrode. So, I don't even think there's a limit to how long they could spin these things for. They just need the mechanism to spin them, right?
Just replace the bearings. That's it.
Okay. Thanks, YD, everybody for giving us. That's PJCnet. Thank you. Okay, we're good.
All right.
They're highly efficient at about 95% and
so efficiency, this is where you can be deceived by numbers. You can have something that's 20% efficient, but if it was cheap and you still get some free energy out of it, there's nothing wrong with that. You're just going to take up more area. You'll just have to have more of this collecting. So this efficiency level of 95% is super excellent. It's right up there with supercapacitors, and I don't know why they say 20 years on a flywheel's life cycle, but so these are the things that we're comparing, right? So the energy density, watt hours per kilogram, they say 200 compared to supercapacitors of 1 to 30. So there's pros and cons of each one of these storage mechanisms, and what we're going to do is document all of it and make sure that we're always selecting the best mechanism for our purpose, right?
Well, yeah, definitely. Well, and what you pointed out there really quick, the energy density here, right? So 200 watts per kilogram, so that's a high number, right? The supercapacitor is only 1 to 30.
Yeah, this
but you're saying this is deceiving.
We're gonna see some other things that'll put this into better perspective with the megajoules coming up in a little bit.
Have a high power density so it can store more energy in a smaller space. And it's because of those advantages that they've been used in things like uninterrupted power supplies for industrial and commercial applications.
So I just want to show people just a simple little cabinet like this, sitting in an office, in a closet, anywhere. This can be your backup, where inside of here there's a flywheel spinning super fast. As soon as the power goes out, boom, you switch over to the power that the flywheel creates for you. So you can have small flywheel setups like this that work for you, and it doesn't have to be megatons big.
Applications to provide backup for essential loads. Flywheels have also been used as control moment gyros in spacecraft like the International Space Station,
right,
to hold the space station at a fixed altitude relative to the Earth's surface. They've been used in motorsports for hybrid propulsion systems and regenerative braking, like the Audi R18 e-tron that won.
All right, so this car right here, it's in this video because they use flywheel technology. So people that want to bag on flywheels like they're archaic and they're not useful, pay attention, because
yeah, the Audi e-tron Quattro
is like smoking everybody.
Yeah, and it's flywheel, right? The e-tron.
Yeah, well, that's part of the system. They've got more, but they definitely use a flywheel to store energy as they're braking.
Won Le Mans in 2012, 2013, and 2014. And they've also been used in the electrical grid to support the increasing spread of renewables. FESS have also been used in grid applications in order to provide ancillary services such as frequency regulation and power fluctuation support. It's similar to how Tesla's Hornsdale Power Reserve has been used in Australia. Some examples are the beacon-powered 20 megawatt units installed in Stephentown, New York,
Hold on a sec.
and Hazel Township,
I just want to bring up here. So they brought up Tesla, and for some reason he's in Australia with a system that spins up flywheels when there's power, and then when the power fluctuates down, it then sends the power out, or it just creates power, one or the other.
Well, the Tesla is the chemical batteries. That's going to be your lithium ion. So they're saying like they did with Tesla there's here in New York, these blue things are where the flywheels set. So instead of having chemical batteries, the blue things are the flywheels that are storing the energy.
Pennsylvania, to support frequency imbalances in the grid. These plants were commissioned in 2011 and 2014. Beacon's flywheel rotor is made up of a carbon fiber composite rim. Its flywheels spin up to 16,000 RPM and can completely charge and discharge for 175,000 cycles. Another company playing this game is Amber Kinetics. Their all-steel M32 model can provide 8 kilowatts of power for 4 hours, achieves efficiency higher than 86%, and offers 11,000 cycles. In 2018, the company, in partnership with West Boylston Municipal Lighting Plant, commissioned a 128 kilowatt, 512 kilowatt hour flywheel energy storage system in Massachusetts. This project is integrated into a grid-connected solar array and has already discharged 116 megawatt hours. Amber Kinetics also installed another storage system, but now in China, to operate a 60 megawatt solar power plant.
So you got the solar power plant, and the way they store their energy there is in flywheels. It's a totally viable solution.
In order to store electricity and improve grid stability. Since it commissioned in 2018, it's already stored 75.6 megawatt hours with no gas emission. But how do flywheels stack up over other energy storage systems? Compared to batteries, flywheels are made up of environmentally friendly materials that can be reused, and they may have higher capacity than lithium-ion and flow batteries. In addition to that, batteries need to be recycled and replaced more frequently than flywheels, which have a much longer life cycle. In comparison to other mechanical energy storage systems such as compressed air and pumped hydro.
All right. So those are obviously some other topics that we're going to be going through at some point. Compressed air and hydro. So hydro, you've got the upper body of water and you've got the lower body of water. And when you have excess electricity, you actually pump the water up into the higher body. And then when you need that extra energy, then you make electricity as you let it back down into the lower reservoir. So just having water at two different heights is an energy storage mechanism. So is compressed air. You just need a big tank and a compressor. You just let it compress. And then when you need to get that energy back, you use the compressor to run your generator to make electricity again.
Flywheels reach higher efficiencies. So what's the catch with flywheels? Why have...
All right, so flywheels more efficient than compressed air and hydro.
We've been seeing them pop up in solar and wind farms everywhere. Well, the latest technology provides energy for just a few hours, and flywheels have high energy installation costs. According to one report in 2016, FESS costs varied from $1,500 to $6,000 per kilowatt hour. And expected installation costs by 2030 will range from $1,000 to $3,900 per kilowatt hour. On the other hand, lithium-ion battery storage systems for utility-scale applications varied from $200 to $1,260 per kilowatt hour, and is expected by 2030 to see a reduction to between $77 and $574 per kilowatt hour. Flywheels are also beaten out by flow battery technology, which may reach between $108 and $576 per kilowatt hour by the same year. Another interesting analysis is the levelized cost of storage, which is directly comparable to LCOE, but for storage systems. In this analysis, the mean for flywheels might reach around $520 per megawatt hour in 2050, while lithium-ion and vanadium redox flow batteries might have a mean between $280 and $220 per megawatt hour respectively. Flywheels need to have a big cost reduction and performance boost, along with the development of new materials with high strength and low density for rotor materials, as well as improvements to the motor and generator itself. This means a lot of money and time spent on research and development, which is why flywheels have been overlooked in favor of the latest battery technologies. But there is an interesting hybrid approach. But before I get to that, I'd like to thank Brilliant for sponsoring this video. If you'd like to learn...
they're not sponsoring us, but at least they help sponsor him.
For supporting the channel. Now back to the hybrid approach. Some recent studies and projects have been developed to verify the feasibility of integrating flywheels with batteries for hybrid energy storage systems. One example is the anti-speed project offered by STRONG Energy.
It's almost over. I know. I should have let it finish. But what I want to point out here is, well, go ahead.
No, go ahead.
Do you want to let it finish?
Well, yeah, they're talking about the combination of flywheels and batteries, what you can do with that, right?
Yeah, well, let it finish, and then I'll say it. I'm sorry.
Energy that's already received about 3 million euros funding for building out a 1 megawatt battery flywheel hybrid energy storage system to support grid stabilization and road. Another recent example is the 8.8 megawatt lithium-ion battery that's been integrated with a 3 megawatt flywheel system in Almelo in the Netherlands. It's going to assist with the integration of green power sources to the grid. These all look to be promising solutions and show that flywheels, although they're an old technology, may be making a bit of a comeback.
They might.
Well, so what I wanted to interject with was that how easy it would be to hook up flywheels along a drive shaft in a car, right? So you have your Tesla driving, and you hook up a flywheel to each tire. You have 4 tires spinning. You can hook up 4 flywheels to each tire. You would never have to charge. And okay, maybe if you were driving 1,000 miles, maybe at the end of that you have to recharge it fully. But having the 4 flywheels, it's so basic to me that we're actually looking at this now. The regenerative braking that you've been discussing is one way, right? So as you brake the car, you create friction, which can then be turned into multiple different ways to create energy, because you have a huge temperature change, huge. When you hit the brakes, if it's raining outside, you can sometimes see your brakes smoke because it's so hot. They get red hot sometimes. You have that aspect. Plus now we're interjecting into the topic, having a flywheel spin. It's almost the same thing as the wheel itself, but what you do is you would hook up a flywheel to the drive shaft, where the drive shafts connect all the way through with the other parts inside the car, and it just makes absolute sense. It's just more evidence that the people that are running the realm right now have done their absolute best to keep us dependent on the most wasteful, ridiculous ways to create these types of vehicles and power our homes. It's becoming abundantly clear, the more that we get into this research, that everything that we should be doing hasn't been done. And in actuality, they're doing it at their cottage and in their vehicles and in their race cars that they want to do their 24-hour race in. Of course, if you don't have to pull over for gas, your car is going to smoke everybody. Right? They were the first one to have, you don't need, so they were somehow able to make the car part electric and part fuel. And so for me, just getting into this, I get very excited because my anticipation of us creating something like this is just, I'm really looking forward to it. Just so, that we could, I don't want to say this, but they need to be put in their place. These people who are in control, that have not done any of the research. Or Jason, you had all these ideas long before we even looked into this topic, and you didn't even study it. So that was my main rant here, is just that combining the flywheel with a car, it just seems like a no-brainer.
Yeah. Well, and there's some other ideas. So, the whole heavy chunk of iron, getting that to your place, having that set up, it seems a little overwhelming. So there's some other companies out there that have some ideas on how to do this. This one right here is the world's largest flywheel energy storage system. And let's see, there was another. Let's see. Let's go to this one first. So here's another twist on it, a concrete flywheel storage system for residential. All right. So just looking at this graphic right here, what you have is an underground vault where the green thing is like, it would have been probably like a plastic shell, like a water storage type tank. And so this vault is put in the ground. It's got its bearings set up, and then they fill it with concrete. So concrete's very heavy. It's very inexpensive compared to other things. And so now all of a sudden you have this massive, super heavy spinning flywheel Right? It's not going to do the high speeds like these other precision ones,
Mm-hmm.
but because of its absolute massive mass, it's going to have incredible energy storage potential, right?
So this basically dreidel looking thing, no pun intended, is sitting on top of a type of a lazy Susan or a spinning tray. And then,
Yeah.
so as they add power to this device, it spins. And when the power goes away, the momentum of it spinning, well, even when it's spinning with power, it's also still generating energy as well because it's hooked up to an alternator.
Well, when power is being put to it, it's taking that and with the speed, with the momentum, it's storing energy. And as soon as the power is not going to the motor to drive it,
It's heavy.
then all of a sudden this mass is still turning the rotor so you can produce the electricity back off of it. So they were saying 95% efficiency. So you're only looking at a 5% loss. If you put, $100 of electric into spinning this up, you're going to get $95 back, is what they were saying.
That's
electricity.
It's a bit of a tough thing to understand, wrap around what you just said. So basically, why would you waste? What you just said was you're going to lose $500 out of 1,000, or no, 100 or 95%. So are you saying
95% is what you're going to save? 5% is what you would lose. So if you had free energy like solar, wind,
okay,
tidal, stuff like that, you would take that energy and store it in here.
You'd spin that thing up with the solar panel power.
Yeah, and you would only lose 5% of it.
So when the sun went down, the time that it took this thing to stop spinning, it would be creating free energy at that point due to its mass and rotation.
You stored up the free energy.
By spinning it, and when it's continuing to spin after you turn the power off, that's where you're gaining your free energy. Is that not correct? I'm confused here.
Get it back.
Okay, so that's the point. And if you had 10 of these, right, then you're talking now. All these things also need to look at how we scale them.
Mm-hmm. So this one takes up roughly 10 square meters. A 10 kilowatt flywheel can be used to store electricity from a residential solar array. France-based startup Energisto was developed a storage technology for residential PV based on flywheel system based on concrete. Flywheel system is able to store electricity by converting it into kinetic energy using a motor to spin a rotor. The flywheel rotates at such a high speed that the electrical power is transformed into mechanical power. Let's see what they have for some stats here. According to the general director, carbon flywheels currently cost around 250 euros per kilowatt. Steel flywheels 200 per kilowatt, and concrete ones only a few euros. Right, so now all of a sudden we're looking at a cheaper flywheel to be able to store the energy. The flywheel is guaranteed for 30 years, and a change of its inverter is expected after 15 years.
That's pretty good.
Yeah.
15-year life? That's great. The cars, what lasts 15 years anywhere now? Anything?
Not really.
TV, washer, and dryer? Okay, go on.
This flywheel has a diameter of 1 meter. It's not that big and weighs 3 tons. So that's the benefit of concrete right there. So the system capacity should be increased initially to 20 kilowatts, then 50, and eventually reach 24 hours of storage. So just another take on the flywheel where you don't have to have this big, massive chunk of metal. You can put this in a hole in the ground, fill it with concrete, have the truck pull up, and then boom, there you go. I think it's a pretty ingenious take. Now this is what we were looking at back when we were originally looking at flywheels. And this is another way of using a flywheel. And this is with a motor and an alternator. And check this out. Right, so this is just regular bearings. Nothing special, no magnetic, no levitating.
It's pretty big, right? We're talking scaled up here.
Yeah. This
is what you were building. This is what you wanted to build.
Yes.
Yeah.
This is what I started, but this guy's got the right stuff. So he's got the right pulleys. They show you the right sizing. Because
this is all tuned. This is what you would have done with the tuning.
Yes. So he's gonna go ahead and continue putting this thing together. Alright, so next phase. He's got his pulleys set up. He's gonna wire in his electrical panel to the alternator. Makes his connections. Now he's got some shore power. So he's got regular electric, and he's going to plug in his regular electric to his electric motor over here. So this motor right here is being powered, and it's driving the flywheel, and the flywheel is storing energy, a lot of it.
Oh, that was loud. It's really moving. That thing is, that's
the speed you need it to be.
It's humming.
So he's got an idler pulley he's got a set. This guy is not worried.
What do you think this guy does for a living? Something with flywheels, maybe? He's got his sandals on. He's not worried at all.
He's not worried.
You know, this is what these guys do over there. I got lots of content where I could show you them do crazy. These guys don't worry. They're in the simulation. They're in it. But he's showing that he clearly built it because he knows every square. He knows how to move around the entire apparatus. So now we got him. Continue, please.
So yeah, he was showing that this power right here is what's turning it on and off. And so he's got a shore power that's powering this motor, but he's pointing to this plug over here because what he's going to do is disconnect his shore power, and he's going to plug this into the output from the alternator.
We've disconnected.
Yeah, you could actually even hear there was a little bit of slowdown in that amount of time that it took for him to get it unplugged and plugged back in. Listen to this.
We'll call this fairing separation. Nominal.
Yeah, listen, there's a little bit of slowdown when it's not getting its power. And it's back. Now it's running off of the power that the alternator is making.
It's a closed loop.
And so he's got a 3 horsepower motor running a 12 kilowatt alternator. He's going to demonstrate the over potential that he has right now. So
it takes quite a bit of power. You can blow a breaker real easy with a grinder. So it's a good demonstration.
So he does that, and then he brings out his welder, shows you that he's got enough power to run this welder.
Would that welder take more power than a compressor?
I'm not sure. So I don't know if this is a 220 welder, if it's a 120. That, I guess it depends on the size of it.
But hang on, I just want to point out something here. whether or not he's using this to weld, he's making free energy now with this machine. Anything that he's able to take off of this and store into a battery or spin a flywheel, another flywheel of concrete in the ground.
Right.
With this device is the motor that spins that. Right? And then you start to multiply things when you add these things together.
Well, my idea is that with a unit like this, it can be running 24/7, and the overabundance of electricity could be used to in an electrolyzer to make as much hydrogen as you possibly can.
Okay, so now you're adding in electrolyzing to this. So this is the power machine you're going to use to electrocute water to make hydrogen, and then you're going to store that into another device.
That would be the thought, because with solar and wind and stuff like that, it's spotty. You have some days that you have it, some days that you don't.
Yep.
But with this thing, once it's running, it runs until there's a mechanical failure.
Well, and also when we talk about solar panel use, we also need to talk about the variations in the temperature. So when it's too hot, the solar panels don't give you as much power, which is you have a huge opportunity with that heat exchange when it's too hot, and when it's too cold, batteries don't work so well, right? And then to take it even, more steps further, learning how to create the hydrogen and then use the hydrogen as the battery. Right? I know I'm probably going too far along with that thought.
So here he does a walkthrough. So in the comments on all these videos, everybody tries to figure out where the hoax is. Where's the hoax? And somebody's going to want to say, "Well, there's batteries in the box.
There's a cable coming up from underneath it in the ground."
Yeah,
that's what they say.
So here's the walkthrough. Obviously, you cannot have enough batteries in this box here to be running the grinder and the welder and all that kind of stuff, and these motors, right? You would have to be running all of it. So you got a couple wires coming out of the motor. They're plugged into that outlet. They had the shore power before. But this is the pulley configuration. It makes some noise. It's not a silent machine. But I sure do love the fact that once this thing is running, it's just going to run.
PJ CNET's wondering, he's suggesting that it would sooner or later have to stop due to the 5% power loss and efficiency.
No, not here. Because the 5% loss is just a conversion. What's happening here is the electric motor right here is driving this flywheel, and the flywheel is storing way more energy, like a supercapacitor would. Plenty that it has no problem turning this 12,000 kilowatt alternator. And as long as a 12,000 kilowatt alternator is spinning with enough RPMs, you're going to have 12,000 kilowatts.
That's a lot.
That's
a lot. Yeah. And it's using the weight and the size of the flywheel. Everything here is super scaled up. This is bigger than what we've looking at. This is bigger. Well, you were thinking a flywheel close to that size.
Yeah, and so this is one of the builds. Turns out now that you can go to places like Alibaba, and this is
just straight up buy one. Come on, I know. Look at this, everybody. The New World Order. If you got enough money, you can just buy these things. They've got it all tuned in. Look at this. Wow, $500. It's not even that much money. What? Come on now. Is that real?
That's what I got to find out.
From Alibaba, huh? Okay.
Because this right here, take a look at this machine. This is...
You could zoom in a bit more. Or you maxed. That's fine.
Yeah.
That's fine. No, that's good.
So that is a beautiful flywheel. With beautiful bearings. And so it's a double pulley setup. You've got...
Double pulley.
A lot of double belts on each side.
Double belt, I see that.
Yeah, and they have so many different other configurations. And look at this. Customized free energy generator, cast iron.
Wow. This is definitely going to be on the shopping cart for Christmas time.
Yeah. Look at the balanced flywheel. Just look at that beautiful spin.
That's nice.
And these are the setups that
Yeah.
people build with them. So
So they've come a long way since we started 5 years ago with this topic, huh? Wow.
They
We
really
we
have.
didn't have this back then. You can see we searched everything. We did it live.
So here's your motor that's going to drive this, and then
Okay.
they've got the pulley sized, and then this one's going to drive the alternator over here.
Double pulley. That's the motor on the right.
Yep.
That's nice. And they sell all that, and there's no way it's only $500. The steel alone will cost more than $500.
Yeah. Well, this says customized free energy generator cast iron flywheel pulley for 40 kilogram, 50 kilogram, 60
Oh.
kilogram, 100. So different sizes. But I wanna figure out-
2,100. I see the price now. That's probably for the small one. Minimum. Your minimum order is going to be 2,100. But if you're getting this thing for 2,100, you can then use this to do the electrolyzing. It's great.
Mhm. All right. So let's shift topics now and go to another one that might be outside of most people's vision, and that is geothermal. What do you know about
I know that that's
geothermal?
not where we live.
Right?
I'm sorry. I have to call it out.
So this guy here, just have a think. He's deep in this energy topic, and he's an absolute chill, heliocentric, and he's not going to take you to the actual truth. But when he goes through some of these texts, he does do a decent job of describing it and what we can actually expect from it. We don't trust these guys completely ever, but let's hear what he has to say about geothermal.
Obviously, but you get what I mean. What we don't see all that often is the stuff going on inside the planet. It can be as deep as 40 kilometres in places. It's still
Oh, brother, no. I'm sorry, everybody on the other side of the screen. I know this
our planet.
traumatizes
It's been
people
there for
because
billions of years.
it's
and it'll most
ridiculous.
likely be there for a few billion more.
All right, let's get down to the
Get
stuff
about
that's real.
35 degrees Celsius hotter for every kilometre.
Okay, hold on. Can we get a pause?
Oh. Yeah.
We can go back again. So 1 second. What I wanted to bring up here is that whether or not you believe the Earth is a sphere or flat, that's on you. We know, we've measured, we've done the observations. There are heat exchanges going on in both models. So what we're looking at here, let's separate ourselves from the ridiculous heliocentrism lies and actually look at the Earth does heat up and cool down. That's what we're getting into now. We're talking about harnessing the changes in the Earth temperature, right? Did I lose you?
Yeah, no, I had a cough, but
That's what we're doing here
temperature differentials.
in the Earth.
Temperature differentials is all you need, and you don't need to have that much. You can actually get by with just like a 6 or 7 degree temperature differential, but the more temperature differential that you have, the more extreme the power is that you can make from it.
North American tectonic plates, and those two plates are actually moving slowly apart, and that's allowing huge amounts of heat from the mantle below to escape into the upper regions of the crust under Iceland's landmass. Most parts of the Earth's crust get about 35 degrees Celsius hotter for every kilometre you go down.
35 Celsius per kilometer that you go down. All right, so the ground warms up the deeper that you go. It's important to pay attention to that.
But if you go down a kilometre below Iceland, you hit temperatures of about 200 degrees Celsius. That powers the famous Icelandic volcanoes and the hot steaming geysers, and it also provides geothermal heat very close to the surface that can be so easily tapped into that Iceland has really got more than it needs. They've built themselves 7 geothermal power stations to generate electricity from the underground energy. They still do it by driving a turbine to rotate an electrical generator.
Turbine to rotate an electrical generator. That's going to be a common theme in a lot of these texts, is that turbine.
Just like a traditional fossil fuel or nuclear power plant, but they don't need to burn coal or gas or fire neutrons at radioactive material to provide the heat to convert water into steam to turn the turbine. They use a fairly straightforward system called flash steam. A borehole is drilled about 3 kilometres deep and cold water is sent down into it.
So borehole, pump down water.
The water gets superheated by the geothermal temperatures and expands into steam, which then comes hurtling back up the other side to drive the turbine.
Okay, hold on.
Pump
Let's slow down here.
water down.
Let's slow down. So we're going to dig holes in the ground so we can go anywhere. Let's say we're the Rothschild family and we want to take over this island. So we go to the island. You're telling me that we dig a lateral hole, or is that lateral just an aquifer in the ground that we're looking at? Approximately 3,000 meters in total width here. At the center of it, is that a pipe?
No, that's just a probably, like you said, like a water table or something.
A water
like
table.
that.
But what we have here is on the right, we have a hot side, and on the right we have the blue side, and on the left we have a hot side. Just holes in the ground we're talking about with pipes in them filled with hot and cold water.
Yeah, this side they pump cold water down underground. Here it flash steams, and then the steam comes up this side and runs a turbine.
Check.
Easy.
It doesn't rely on the weather conditions. It's always on, so it can be used for constant and predictable baseload power.
Perpetual motion machine. Earth.
Emissions. All that cheap electricity has allowed Iceland to develop a thriving aluminium industry that now accounts for about 40% of the
Aluminum industry. I didn't catch that earlier. That's an important one to know.
Because you can use aluminum in reacting.
Mm-hmm.
island's exports, turning Iceland into one of Europe's richest nations. They also pump geothermally heated water all over the island in a network of heavily insulated pipes to provide district heating for homes and businesses, and greenhouses that supply a rich variety of healthy food for the population. They've got so much spare hot water that they can afford to heat outdoor swimming pools all year round, and even pump some of it into freezing lakes to keep bits of it warm enough for the fish to survive through the coldest months of winter. But on a global scale, geothermal energy only accounts for about 1% of total electricity capacity.
Why?
So why aren't we embracing this seemingly inexhaustible carbon-free natural resource more enthusiastically? Well, the answer is that some countries are going for it, but most of them are located on or near to the fault lines where tectonic plates butt up against each other. Of the 20 or so countries currently generating geothermal power, the United States is the largest, producing about 2.5 gigawatts.
Yeah, I wonder how much that's Hawaii.
With 725 megawatts coming from the world's largest
Just saying. And Yellowstone.
geysers, located in the Mayacamas Mountains, about 30 miles north of Santa Rosa in California. Then comes Indonesia, the Philippines, Turkey, New Zealand, Mexico, Kenya, Italy and Japan. In 2018, the International Energy Agency predicted growth of as much as 4.5 gigawatts in geothermal energy production.
Let's skip ahead here a little bit.
Then turns to vapour to drive.
All right, so natural aquifer. Let's understand there's different styles of geothermal. So we saw the one pump the cold water down, take the steam that's coming back up, run a turbine.
I can't.
Would need to grow.
Go ahead.
I don't like the way they have the initiatives laid out here. It reminds me of the stupid New World Order Agenda 2030. Sorry to point that out. Forgive me, everybody.
Sustainable development.
No, it is. It is. Oh, I'm sorry, everybody. I didn't mean to traumatize you.
Grow by more like 10% per year between now and 2030. But to reach that target, geothermal energy needs to be adopted on a truly global basis, which means finding ways of tapping into our
realm wide.
all the other countries of the world that aren't fortunate enough to be located above fault lines. A system called binary power is an alternative to the more traditional flash steam system. In a binary system, hot water from a naturally occurring underground aquifer is pumped up into a heat exchanger where it gives up its heat to a secondary fluid that has a much lower boiling point. The secondary fluid then turns to vapour to drive the turbine. The beauty of this system is that it only needs the water to be at about 100 degrees Celsius, so in theory you don't need to drill so deeply to hit the right temperature. And that makes it a system that could be used by many countries regardless of their location. But you still need to get at the hot water, however deep it may be, and you still need to ensure that the supply doesn't run out. And that brings us to the increasingly contentious subject of enhanced geothermal systems, or EGS. The United States Office of Energy Efficiency and Renewable Energy.
All right, that's enough of this one. He's got a little bit more information in this video on geothermal ground source heat pumps, heating your home from your own backyard. So what we're just looking at is the industrial, utility level type geothermal. Now what about something that you can do in your own backyard for your own house. Let's check this out.
About geothermal heat energy, you'll know there's an awful lot of it right under our feet in the Earth's crust. The challenge is to get at it in a safe, environmentally friendly and economic way so as to produce a large-scale transfer of heat into a liquid that then turns into vapour and moves across a turbine to drive an electrical generator, which in turn provides extra power for national electricity grids. And many
All right, let's jump ahead to here.
during the colder months. And that basic fundamental physical property is what makes ground source heat pumps such a simple and effective solution. Here's how they work. A mix of cold water and antifreeze is pumped through.
All right, so
Okay, yeah, we're on to a new one now. Okay, go ahead.
now we're not 3,000 meters or 2,000 meters below ground. We're just below the frost line, right? So now all of a sudden you have pipe in your backyard with some coils where you have the same process that's taking place with your air conditioner, right? But what you're using is the temperature of the ground versus the temperature of the air, and using that difference between the two, where this can create both heat for your house and cooling.
Yeah, you've got the evaporator side and the condenser side. It's the same thing that goes in an air conditioner. You have the two coils, right? And so what you're showing me here, I just want to get this on layman's terms. We don't have to drill close to hell, right? The other ones, we got to get pretty damn close to hell. Okay, we got to get big digging 1,000-foot, pipes down there. That's a lot of work. This one here is like 30 feet deep, maybe. I don't know. I'm guessing. And it's looped water pipe. The water does its loop and it goes through its cycle. And when it comes through the evaporator and then down through the expansion valve, it creates heat. And then the condenser side then takes that heat and translates it into energy. Is that right? Or steam? What is this one incorporating steam?
No, this is just like your typical AC heat pump air conditioner.
Oh, this is just to cool the building. I got it now. Thank you. I'm with you.
Yep.
Through a ground array of energy absorbing pipes, getting constantly warmed by the ground's low grade heat as it circulates. The warmed up mixture then gets fed into a heat exchanger, otherwise known as an evaporator, where it transfers its energy to a secondary fluid with a much lower boiling point. And that fluid then turns to a gas, which gets compressed to increase its temperature still further. The hot gas then flows into a condenser, where it dumps its energy into a space heating system, or even to provide the hot water for the building if required. Once all that energy has been transferred out of the gas, it turns back into a liquid and goes through an expansion valve at the end of the cycle to reduce its pressure and temperature back to the starting point. It's a completely closed loop cycle, so the fluid just goes round and round, absorbing energy from below and dumping it where it's needed. Not all homes and buildings have huge expanses of space around them, of course. In those cases, rather than winding the energy absorbing pipes around in a horizontal array about a metre underground, they can be sunk about 100 metres vertically downwards, like this system being installed by a company called NGO out in California. For each kilowatt of energy consumed by the system, 4 kilowatts of heat energy are generated, effectively reducing the cost per kilowatt hour by 75%.
Reducing the cost per kilowatt hour by 75%. So anybody that needs heating or cooling in their house should be looking at geothermal, because this system right here takes 75% less energy to heat and cool your home, right? By using the ground.
In hotter countries that normally use air conditioners during the summertime, the stable ground temperature will actually be lower than the hot summer air, and that means the whole cycle can be reversed so that excess heat from the ambient air in the building can be transferred into the system and sent back through the cycle to be dumped into the ground via the pipe arrays, turning a heating system into a very efficient cooling system, saving between 20 and 40% on the electricity bill for a traditional air conditioner. In most cases, the ground source heat pump is combined with a more traditional water boiler to ensure there's no risk of the home lacking heat during extreme weather events. But even if that boiler is heated by fossil fuel, there is still a large reduction in CO2 emissions over the lifetime of the installation, because the vast majority of the work...
Klaus, have him say that. But I do find this very fascinating. What you've now introduced is the home user. So you can dig a hole in the ground and put these pipes in, and you can heat and cool your house off this. You could probably create a hockey rink doing this type of system. This is how air conditioning works, right? It's very interesting stuff.
Yeah, let's see some practical setups.
Some video over at the Fully Charged channel looking at Moonstone House in the UK, which generates more energy than it uses and is actually fitted with both horizontal and vertical geothermal heat pump systems. According to this article by Molly Lempriere, published on the Current News website in September 2020, here in the UK, while decarbonisation of electricity has steamed ahead, it seems heat has often been forgotten. The sector generates about 37% of total UK carbon emissions when you add in industrial processes, so Lempriere argues that now is the time for action if the country is to hit its net zero target by 2050. But while the technology is now mature and well proven, governments have not been willing to provide the sorts of subsidies and grants that are really needed to kickstart the transition for most individual domestic consumers. The power of the fossil fuel lobby is still extremely
That's
back in 2017. They're called ISO Energy and are the UK's most experienced consultants and installers of renewable energy systems. I asked them to run through some numbers based on my fairly typical 3-bedroom Victorian terraced house with a garden out the back. First and foremost, ISO advised that a horizontal system isn't suitable for a small garden like mine, so they based their numbers on a borehole installation. A 9 kilowatt system, including the cost of drilling the boreholes, all the internal componentry and a full-size hot water storage tank, from first survey to full installation and commissioning, comes in at about £26,000. A retrofit here in the UK has reduced VAT rates of 5% instead of the normal 20%, so we still need to add another £1,300 onto that to take the total to just over £27,000.
He's talking
But I also
taxes and
explained
everything.
that the domestic renewable heat incentive can earn the owner of a system like this as much as £4,000 a year for the 7 years. So you're looking at a payback time of about 7 years, which is actually slightly quicker than the payback on the solar power system.
All right. So it's an important point. Payback on geothermal 7 years, and he's saying that this is actually a little bit faster than solar.
Okay.
Right, so
it's better than solar. And could we reduce these prices if we install this ourselves?
of course.
How much of these are, man hours building?
Yeah, it's just a bunch of pipes, a closed loop pipe system. So the borehole is a tougher one. You need to have the drilling rig, but otherwise you can just dig trenches and lay loops close to the surface if you've got enough ground area. So each system has to be designed for its setup. But yeah, it can be done way cheaper. In fact, I watched a number of YouTube videos about guys that did this themselves and had just a fraction of this cost in it and are super happy with their systems.
That I've had since 2017. The obstacle, of course, is that the homeowner has to pay for the system up front and claim back the incentive.
All right, so there's geothermal. Let's move on to another new, well, this is an old tech, but let's talk about a tech that most people probably haven't heard of, and that's solid state batteries. All right, so U.S. battery maker unveils solid state storage systems for residential applications. Amtricity has emerged from stealth mode with plans to manufacture solid state batteries for residential. Yes.
So we're talking about like solid state computer type systems. Now we're saying we have solid state batteries. Okay.
Solid state.
Okay.
So
I'm with you.
Here's a 12 kilowatt hour residential unit.
Kilowatts. That's a lot of power.
It is.
Wow. That big, right? That's not that big.
It's not that big.
Size of a fridge?
Mini fridge. All right.
It's
Not a
probably
big fridge.
30 by 30 by looks like 4.5 feet maybe.
Mm-hmm.
A couple Joe Rogans tall, right?
So this company was founded in 2020 based in Florida. Plans to build its first U.S. manufacturing facility by 2024. They're looking at Texas, right? They got to be.
Figure they're looking at Texas. Come on.
Yeah. All right. So its proprietary solid state batteries include a cell capacity above 500 amp hours. That's a lot. Up to 3,000 amp hours with an 11,000 deep cycle discharge cycle. So this doesn't really tell you a whole lot about the solid state batteries. So let's keep looking. So this is the company, Amptricity. It's changing how humanity uses energy. So here's their pros for it. Higher safety margin. There's no thermal runoff. Highest energy density in the industry. So these are the important numbers: 377.55 watt hours per kilogram. Wide operating range, -40 to 131. That's pretty much, I don't want to be outside of that operating range. More charge cycles. So another energy storage solution. The problem with current lithium ion batteries is they say short lifetime, high land costs, high insurance costs, high operating costs, high installation costs, air conditioning required, high maintenance costs. Quality, they're toxic, they're flammable, high footprint, shorter life expectancy, overheat, expensive casings, lower energy storage efficiency. Their energy density is low. They underperform in extreme temperatures. They have thermal runoff and low duration discharge rate. Now, the solution, the solid state battery. So large capacity, they're saying 500, 750, 1,000, 1,500, 2,500 amp hours, 3,000 amp hours. So full charges, lower installation costs, lower operating costs, lower land costs, lower insurance costs, lower maintenance costs, no air conditioning required, smaller footprint, cell level control, 100% recyclable and non-toxic, operates underwater, long life expectancy, high energy storage efficiency, non-flammable, non-explosive, ultra-high discharge. So remember what happens with the lithium ion batteries when you get them wet, right? All those Tesla cars
They go
that
boom.
went underwater. Not with the solid state. All right. So we're hearing pros and cons, but we're still not learning a ton about them. So here's an article on faster charging and increased range, solid state batteries for EVs explained. Many think this lithium ion alternative will nearly double vehicle range and reduce charge time, dramatically changing the perception and performance of electric vehicles. So this just came out on November 11th of this year. This is pretty fresh stuff here. Many aspects of an electric vehicle are the same as a gas-powered one. The seats are seats, tires are tires, steering wheel, blah, 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 blah. This alternative to the lithium-ion batteries used today promises to improve vehicle range, decrease charge times, and eliminate the risk of fires. Honda recently confirmed it's working on them in its Tokyo-based lab with plans to launch a vehicle with a solid-state battery in the latter part of by 2028 or 2029. Hyundai, BMW, Ford, GM, Volkswagen are more conducting similar research. Toyota leads with over 1,300 patents related to solid-state batteries, and it plans to launch a hybrid one by 2025. So here's your lithium-ion battery, and here's a solid-state battery. Let's learn more about them. Solid-state batteries operate the same way as any other battery. They take energy in, store it, and release the power to devices, from Walkman to watches, and now vehicle motors. The difference is the materials inside. Lithium-ion batteries used in EVs today have a liquid electrolyte solution sandwiched in between their cathodes and anodes. See the middle gap in the image above. Alternatively, solid-state batteries use solid electrolytes. The increased density means solid-state batteries can hold anywhere between 2 to 10 times the capacity of a lithium-ion battery. 2 to 10 times. So at worst, it's double. At best, it's 10 times as much. Why don't EVs already use solid-state batteries? Solid-state batteries already exist, just in much smaller devices like smartwatches, pacemakers, and RFID tags.
Oh no, come on. Oh,
They've already had this tech for a long time, right? The barrier to using them in EVs is primarily that they're expensive and difficult to produce at a large size at scale. Longevity is another issue, but Honda says it has a solution. The solid electrolytes can degrade over time, so Honda plans to protect it by wrapping it in a new polymer fabric. So here they're in the process of making a solid-state battery. Do they increase range? With a solid-state batteries, EVs should be able to go just as far as a gas-powered car does before refueling. Take a 15-gallon gas tank that goes 30 miles per gallon, for example. That car can go 450 miles before filling up. Most EVs today have ranges of 200 to 300 miles, although the Denali will have a 400-mile range. Multiplying those ranges by about 50% or as much as 80%, solid-state batteries are ready to play ball on road trips. An EV with a 300-mile range now has 450 miles. Plus, solid-state batteries will charge faster than lithium-ion with less degradation to the battery itself. No more battery fires.
sorry.
Right?
It just shows again that they rolled out Elon Musk with the nonsense version of what we really needed. Again, I'm triggered.
No, and then there's the recycling. These things can be rejuvenated. You can refresh the battery if it's been losing its potential. And so they contain nickel, manganese, lithium, and small amounts of cobalt. Same methods for recycling lithium-ion batteries by extracting these metals will also work for solid-state batteries. So they are recyclable. So they're 2 to 10 times more powerful, safer, and they're environmentally friendly too. They're recyclable. But let's move on to another tech. So
where are we going?
we're going to go to sand batteries. All right. We're going back to this other guy, how a sand battery could change
Hold on.
the energy game.
So we went from drilling holes in the ground. First, we went flywheels, holes in the ground with water, and using an air conditioner system with the earth as the temperature varying. And then we went on to solid state batteries. Now we're going into using sand. Just sand. Okay, I'm with you.
So
I'm with you.
This came out 3 months ago, so it's not terribly old. And so here's another energy storage solution.
As you know, energy efficient storage systems are the conundrum of making the most out of our intermittent renewable energy generation. Now, unless you've had your head in the sand, it's a glaring problem that we have to solve, which is why so many different battery technologies are being explored and developed over the last few years, to the point that some are now coming out of the sand. That's what recently happened in Finland, where the world's first commercial sand battery went live this past July. But how does it work, and is it a viable path for storing energy? Let's see if we can come to a decision on this. Before digging into the sand battery, we should first warm up on some background on thermal energy storage, or TES, which is the technology behind this new invention. Now, if you watch my videos on a regular basis, you've probably noticed that I'm on a bit of a hot streak recently. Now, I've talked about some heat storage before with phase change materials and molecules, as well as concentrated solar power plants. Chemical storage isn't the only option we have to stock up on renewable power.
All right, so that's an important point. Chemical storage is not the only way. So we went through the flywheels, like you said, because that's not chemical energy storage. This right here, the flywheel is not chemical energy storage, and the sand battery is not chemical energy storage, but it is energy storage nonetheless.
You can convert renewables into heat and store that instead. In other words, you could have a thermal or heat battery. But why should we care about storing
I already see it.
The Energy Information Administration, or the EIA, heating along with cooling and ventilation accounted for 46% of US buildings' energy demand in 2021. Yet this power comes from dirty sources. Over 50% of new American homes still rely on natural gas for space and water heating. Also, based on a recent study, warming up water in houses and offices and fueling low-temperature industrial processes, such as brick and food drying, releases about 10% of US energy-related CO2 emissions. So you can see why developing more thermal storage units will reduce the reliance on fossil fuels, which can also help shrink the climate impact of our heat consumption. So how does this technology work? Well, sensible heat storage is currently one of the most widespread TES solutions. Basically, you heat up a liquid or a solid material by harvesting wind or solar energy during the day or in the summer when there's plenty of it. Now, the typical way of doing this is to pass electricity through a heating element in contact with your storage material. And to discharge the heat, you simply lower the battery temperature by piping in cool air. Your heat transfer medium can be something as simple as water or more complex compounds like molten salts, which are typically integrated into concentrated solar power plants, or CSP, just like I covered in a previous video. One of the main reasons we need to develop more energy storage facilities is to minimize curtailment for renewables like solar and wind. That's when we have more energy output than demand. A good example of that is when you see wind turbines standing still on a windy day. They've been turned off because there's no demand for the energy that's being generated. As predicted by the Australian Energy Market Operator, over 20% of renewables will be curtailed by 2050. That's why TES systems could play a role in getting us out of hot water. The Sweden-based utility Vattenfall will soon fill up a 45-meter or about 150-foot high tower with water in Berlin. And fun fact, the volume of water sitting in their tank would fill up 350,000 bathtubs. Although I don't think you'd want to take a bath in this tank. Their battery is next to a power-to-heat plant that harvests spare wind energy from the grid to heat up the water to just under 100 degrees Celsius or 212 degrees Fahrenheit. Now, it's expected to be up and running in April of 2023. Their giant thermos will keep water hot and supply it for up to 13.
So it's a giant thermos, right? We, for the job site, we've got a 1 gallon double wall insulated thing so that we can take coffee with us. So we are storing heat energy portably, taking it with us to the job site. But here's a big tank for storing
That's
heat
massive.
energy.
Wow, that's huge. Wow.
This is a
hours when
water
needed.
one.
And this sounds promising, but what if we could clean up our dirty heat by using dirt?
Sand, yeah.
Before we get to
I saw
that,
the
though, I'd like to
picture.
thank Aura for sponsoring this.
So in the picture that I saw, let me just try to guess it because I haven't seen this.
Yeah.
It looks like they channel the heat into the sand, and then as the sand cools, they harness power from that.
Exactly.
Yeah, that's right. Okay.
Yeah. It passes ad.
Sandbox, a 23-foot tall or about 7-meter steel silo containing 100 tons of low-grade sand and a bunch of pipes. But they're not using this storage medium to build a sandcastle in the Finnish polar night sky. After running a 3 megawatt-hour pilot in Tampere to heat up a couple of buildings, the startup fine-tuned their design and scaled it up. Teaming up with Vanjankoski, which is Kakanpa's district heating network operator, and I hope I didn't butcher those names, a larger battery is already heating up local homes, offices, and even a municipal swimming pool, which is serving around 10,000 people overall.
Hold on, I wasn't right. Hang on, I just want to get a pause. They're not creating energy. They're moving heat to other areas. Okay.
Saving the heat, storing it because
It saves money on heating.
well, they can use it to they can take that heat and convert it directly to electricity too.
This anywhere in the world where you have a district heating infrastructure, just like in New York, Boston, Philadelphia, San Francisco, Denver, Minneapolis. Pretty much most major US cities have one. As touted by Polar Night Energy, their latest battery model could store up to 8 megawatt hours of energy as heat. Aside from the environmental benefits, this storage solution allows the city to save money. Winter over there seems never ending, and Finnish temperatures can be nearly as low as those in Alaska. As you can imagine, the huge heat demand during the long cold season translates into high costs. On the other hand, the sand battery will store clean power during the summer when it's readily available, and then reuse it during the long winter when there's little sunshine. That's why digging into it is financially handy. Nowadays, this would have a higher impact than ever. In fact, after a recent payment dispute last May, Russia froze their gas supply to Finland, so you can probably see why they need a lot of low-cost heat to keep themselves warm. Local governments are pretty pumped on the idea and want to make it 1,000 times bigger. But how did Polar Night Energy turn a sand-filled tank into a heat-storing battery? Well, being connected to the grid, the battery receives excess solar and wind-produced electricity as input. Then this is converted into heat and transferred to the sand. To be more specific, the renewables power a resistance heater which heats up the air, which is then circulated around the sand through a series of pipes. Now, although it may sound complicated, their heat generation relies on resistive heating, which is basically how common appliances like toasters work. As claimed by the startup, their reservoir is well insulated from the outer environment, which minimizes heat losses over time. Reaching temperatures of up to 600 degrees Celsius or over 1,000 degrees Fahrenheit.
That's a lot of temperature right
That's
there.
hot in there. I didn't expect that.
Yeah, that's some serious heat.
Their sand-based unit could retain heat for months. When it's time to deliver it, you just blow cool air through the pipes inside the hot sand bed. The end result you have coming out of the system is hot air that can produce greener steam for industrial processes, heating public water, or homes. Now, clearly, something as simple and safe as sand to store green power is hot stuff.
And you know, he gave something out.
Other storage.
He gave something out there. So how much does steam give you in an energy way? So when you make steam, what's the compression ratio to it?
1,700%.
It's not a compression ratio. That's the amount of
It's the
pressure.
expansive force that it has.
Thank you.
Because
how much?
is it
1,700 or 17,000? Let's look it up.
700?
So that he just gave away that when you can create steam. See, steam is another free energy type technology that they took away because it was too powerful, right? You can do anything with steam. You can have a giant battleship cruise 1,600 times. So right there, you're mega boosting. So if you could create steam with this type of system, you can then super boost it with what you can do with the steam. Right. So I find that to be one of the biggest keys here.
Let's go back to this.
I want to combine all this and steam.
Yeah.
Simplicity is one of the top benefits of sand-based heat batteries. As stated by the startup's CTO, it's really a typical silo which can be built in any steel workshop. Now, crazy as it sounds, they won't need to build any factories as they scale up. Obviously, they need further components.
So hold on.
Pipes, pumps, fans.
So instead of just a water tower at the top of the hill, there should be a silo filled with sand that we're all using to heat our places.
Yeah, well,
And power.
it's a way to store energy. All right. So when you have excess heat, you store it. When you have excess power that you're making, you store it. And then when you need it, you can, like, he said you blow the cool air into it, and next thing you know, you've got power coming out.
Heating elements, you get the idea. But these are all standard equipment readily available everywhere. Same applies to their key ingredient, which is sand. This is a key advantage over conventional chemical batteries, which rely on hard-to-mine materials like lithium, nickel, and cobalt.
They're at the beach.
Energy could use any type of sand from
What's that?
At the beach. You don't have to dig down far for this stuff.
No, there's plenty of sand. There's no sand shortages in the world.
No.
any location. The startup prioritizes upcycling the sand discarded in the construction industry, which helps to minimize waste. And that's not the only environmental bonus. As estimated by a third party, Mission Innovation, based on the Avoided Emissions Framework, Polar Night Energy's sand battery could have...
This is all about the CO2 stuff. What else does he got? Here's...
use that stored heat to drive a steam turbine, but that would add an extra step butting into the round-trip efficiency.
We got
drastically reducing it from 99%.
That was an airplane type engine.
Now,
A
this
fan
is miles
blade or
away from
whatever.
lithium-ion
Turboprop.
batteries, facing only a 5%.
It was a turbo
Right.
prop that you have in power plants already.
Energy loss during their operation. So rather than turning it into electricity, it would be more environmentally and economically suitable to use the renewable heat as is. For instance, we could tap into it to replace natural gas fueled boilers for warming up our buildings. But this would only make sense in cities where you have district scale infrastructure. In addition, the green P2H solution could also...
Yeah, so this works on infrastructure. But
He's got his YouTube badge behind him, huh?
yep.
On the wall.
But an interesting way nonetheless for
Yeah.
storing energy, right?
Stepped it up again. Thank you for that. I enjoyed that section as well. So, because that sounds very usable, like anybody, I think there's pretty much sand everywhere. I think it's everywhere in the realm. I don't think there's anywhere where there's no sand, really. Wow.
Right? And I've got one more breakthrough tech. So this came out November 24th, 2022. This
Hey,
is
wait a minute.
pretty fresh.
I keep interrupting you. Forgive me for that. I'm just having fun here. Is that the thumbnail picture?
It is.
Yes, I got it. Thank you. That's all I have to say.
Yes, a light powered catalyst could be key for the hydrogen economy. So we've talked about electrolyzers, we've talked about chemical reactions, and now we're adding light as
Wait a minute. Hold on. Flywheel. I'm not going to go through them all again. But now you're saying that we can use light to create hydrogen.
Mm-hmm. So to release it, yeah.
So I do know a YouTuber that was constantly talking about when you electrocute. I didn't know about the light though. That's interesting. Okay, take it away.
This is new. This is November 24th, 2022. So it says Rice University researchers have engineered a key light-activated nanomaterial for the hydrogen economy. Using only inexpensive raw materials, a team from Rice's laboratory, blah, 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 created a scalable catalyst that needs only the power of light to convert ammonia into clean-burning hydrogen fuel.
What? Where do we find ammonia? What is it, 9 million gallons or something created by the Americans? We create ammonia.
We, the peers, right? So the
humans and animals, all of us.
Yeah, the nitrogen mixed with the hydrogen is what creates the ammonia. So now you've got the ammonia, and now all of a sudden you just need light in order to release the hydrogen. Check this out. The research follows government and industry investment, blah, blah, blah. The pace of chemical reactions typically increases with temperature, and chemical producers have capitalized on this for more than a century by applying heat on an industrial scale.
Okay, hold on. So where we have the solar panel problems when it's too hot, the solar panels aren't very good. They're good in the cold, but they're not very good in the heat, right? Or is that true?
Right.
So, but this here is saying the hotter it is, the better it is to do this.
Yeah. Let's check out this video here.
This paper boiled down to an amazing discovery. We were looking at a very important reaction, ammonia decomposition. This is very important for the hydrogen economy. And we started by working with our antenna reactor nanoparticles. So these are particles that are activated by light, but they do chemistry. And they can convert a catalyst, a well-known thermal catalyst where people use heat. They can convert the thermal catalyst to a light-based catalyst.
Well, catalysis is the foundation of chemical industry, and that's one of the most energy-consuming parts of all society. The catalyst makes the chemical transformations easier.
We started the experiment by using a copper antenna and a ruthenium reactor. The ruthenium is where the actual chemistry happens. And then my student had a really clever idea, a kind of crazy idea. He said, instead of ruthenium, which of course is very, very expensive, why don't we try iron?
So my whole work is built on
iron, right? Let's try iron.
This ideology that we want to not only do a reaction that is beneficial, but also find a catalyst that is much more abundant, much more cheap, much more sustainable than what we had before.
So that's the first innovation we do here. We show that catalysis can be done by these very cheap and abundant materials, sustainable materials. Perhaps even more important is that we can do this with light. Okay, so we don't have to heat up a reactor. The heating up of a reactor is a very slow process. It requires very high-grade materials, high pressures, high temperature. When we do it with light, we can basically do it in a very small, we could do it in a plastic container, obviously we don't do that, but we go to very
You could just do this in a little plastic container, right?
low temperatures and very low pressures. So it's a very sustainable, it's a very little investment in that kind of equipment. Perhaps even more important when it comes to hydrogen, which is the focus of this science paper, is that we can do it on the fly.
Because you're using less energy, this could also enable decentralized plant, and this decentralized plant actually can produce hydrogen which depends on the need of the customer. In terms of like a near-term goal, we are trying to deploy this technology in different parts of the world to produce clean hydrogen. For example, a CZG plasmonic joined an agreement with Lotte Chemical and Sumitomo Corporation to deliver fully electrified ammonia cracking plant to help South Korea to decarbonize.
And this is being developed in Syzygy Plasmonics, which is a company that Peter and I co-founded. So this type of technology is being used to drive chemistry based on our antenna reactor nanoparticles, our antenna reactor complexes. And so we show in this work that LED-based chemistry is actually doable, and it's doable at scales that can actually contribute to industrial scale chemistry and industrially important reactions.
All right, lots of word salad, but the last thing that she said there is that this LED technology can be done at the big scale. So it also demonstrates that photocatalysis can be efficiently performed with inexpensive LED photon sources. This LED lights. The low-cost hydrogen that could be produced locally rather than in massive centralized plants.
So they're taken into a local scale.
Yeah. Plenty of word salad, but you've got a reaction cell, you've got the light shining in there, and with the catalyst that they're using with the ammonia, they are releasing the hydrogen out of the ammonia with these LED lights.
So they're putting iron shavings with ammonia in a tube, and they're shining a bright LED light on it. It's boom, hydrogen comes out.
Hydrogen. Exactly.
Okay. Yeah, this is interesting. This one seems a lot more complicated than, heating up some sand with some pipes. But yeah, I'm interested in this too. It looks really high-techy and all, like fusion.
Cool because
right? It's fusion.
These LED lights on, right?
Yeah. It's interesting. I like this one too. Anything that we're talking about using light. Can we harness the power of the sun in one of these containers and just bubble out hydrogen and ammonia that way too? I wonder.
Probably. Well, I've got a couple more tabs, but I think I might save those, brother.
It's up to you. If you want to save them, you can. If you want to keep going, it's up to you. Yeah, I enjoyed it. I enjoyed tonight.
These were just some tabs that I've collected over the last week or so that I didn't know about sand batteries. I didn't know about LEDs. Cracking off the hydrogen and ammonia, right?
Yeah, fusion. No, anti-fusion, right? It's cold fusion. Nah, I don't even want to get into this talk. So, hey, I got an idea.
It's like photoelectrolysis.
Photoelectrolysis. Okay, I got an idea. If there's anybody tuned in right now, if you have any questions that you want to put in the chat, anything that you're interested in, I know PJCNet's been active in there, and YD, obviously. Let's just field some questions, right?
Sure.
I thought you went through it, so you're just saying these were some tabs of the types of free energy. We got to change. I know this free energy term. You've got me all changed my mind. When I hear it, there's like, okay, energy storage and creation devices. Not free. None of it's free, right? You got me thinking this way in my head now. So I enjoyed the run through. People might be thinking of questions or anything that they wanted to add. Can we quickly go back to the first? I just want to do a quick run through of all the different tabs again, just so I can have it clear in my mind what we went through and what we were talking about, starting with the flywheel, right?
Yeah. So we started with kinetic energy storage systems.
Spinning metal or concrete,
flywheels.
Anything. You spin something, and then when the power turns off, it keeps spinning, you make power off that.
Yeah. So they had buses back in the day with flywheels in them.
There's that technology.
Have them.
Yeah.
Right.
They probably do. They probably incorporate this in places. We just don't get to see it.
So you got, solar, you've got wind. You take that electricity, you store it in a rotating flywheel. And it's a very viable storage solution.
Mm-hmm. That was one.
And then geothermal, you use the temperature difference between Earth and air.
Okay. Or using Earth's temperature changes, number 2.
Mm-hmm.
I like that.
And now there's once we get in, there's ways to actually take that temperature difference and produce electricity from it directly.
Directly. That's interesting.
That'll be a whole nother topic. But so geothermal is another thing that you should have in all of your
Builds.
designs.
Yep.
Yep. And then solid state battery.
That one's called RHI. Okay.
I had not heard of
Solid
solid
state.
state batteries.
Boom.
Solid state, yeah.
Much better. And the key points that I want to remember here was that they can recharge faster. You can revamp them, right? So you pour a little distilled water in your car battery. It lasts a little longer. This thing, obviously, you can do the same thing. They charge quicker and they have 10 times the power. Am I right?
2 to 10, they said. So,
Oh, I always want to go with the max.
yeah, double to 10 times. And
Okay, that's 3.
then we went to the sand battery. Sand battery is a neat idea. I like it. Sand is plenty of it.
Yeah, it's everywhere.
Store your heat in here.
I mean, I guess it's not everywhere, but we do live on an island realm. So at the edges of most of the islands, if not all of them, you can find sand. China's building whole islands out of sand that they're just dredging out of the ocean, right? There's an abundance of sand. So sand is 4.
If there's not enough sand above the on dry ground, you can
Yeah.
always dig up the sand that's underwater, right?
Dredge it out. You can do it easy. Boom. They have the machines. So that's 4 different technologies now. Energy and energy storage.
Cracking the hydrogen out of ammonia using light. Right. So now all of a sudden you're using electric to run your LEDs, but you're not using that in electrolysis where you're drawing these huge amperages, right, in order to crack the hydrogen out of the water.
Mm-hmm.
Here you're working with ammonia, which has, it's got a heavy load.
It carries more hydrogen than hydrogen can carry on its own.
Yes. 1.5 times.
Good. Okay, I'm with you.
And so yeah, using light and LEDs, they're efficient, right? Everybody's been switching to
Yeah, they work really good. Yeah. We just got a bunch of them in our studios here.
They figured out how to make really efficient lights with LEDs. So it's not going to be very power consuming.
So that's 5 different energy storage and creation systems. And some incorporate hydrogen. You've got sand. We've got spinning metal and concrete. Flywheel metal just spinning. So I think what you've done here is you've given a good introduction into the multiple systems that need to be employed on a home level to utilize all the different things, because we can't just have one windmill because it's ridiculous, right? We can't just have the one tide machine that's in the water that's spinning when the water comes in and out. And the solar panels, everybody knows we went over that. They're some of the worst technology that's ever been,
They're
created.
getting better. Don't
Okay,
we're not gonna
correct me.
bash solar like it's. We're not going to bash solar like it's the worst. Their efficiencies are going up. The cost of the panels are going down.
Mm-hmm.
Their longevity is increasing.
But there's more there. There's more there.
more.
That's all I'm trying to say is they're holding back.
And we don't even have to actually, those panels don't have to be just collecting the light energy. Right. Right now they're photovoltaic, but you can also heat. If you had that panel up on the roof, just having the heat on it, you can actually create electricity from that too. So those are the Peltier devices that we'll be getting into down the road.
Peltier is a bike, right? So you did skip the thermal Earth diagram. We didn't see that in your run through of what we went through. How you can turn the Earth into an air conditioner system by having simply a coil. You didn't show that graphic. That was for me. That was one of the best things because everybody can dig a hole in the ground. It's not that hard. Think of what they had to do to get water before we had these real. Here it is, the evaporator side and the condenser side, and then digging the hole in the ground. This is very interesting stuff. This is way smarter and way cleaner than any other ways to create heat and cool, right?
Yeah, no, with my own property, I would absolutely 100% want a geothermal system for heating and cooling. It makes absolute sense.
Yeah. I mean,
Makes absolute sense.
and you can turn this into steam, and then you get 1,600 times the expansion, which then you can super boost whatever thing you have. YD's pumped in with an interesting comment. She says wind turbines are the worst option. They require 12,000 gallons of oil a year to operate. That's a lot of black goo that needs to go into that thing, right? Maybe that's all they use the black goo for, Jason, a lubricant.
Yeah, I mean, black goo has its place.
Don't down talk black goo now.
Well,
I'm kidding.
So give people an idea of, here's energy storage systems from Wikipedia. I'll show you. All right, so energy density. We're always going to be looking at where can you store the most amount of energy. And this first part starts out with some nonsense. We'll scroll past antimatter. They've got numbers.
What? Antimatter? What do you mean anti? How are they measuring something that's anti-measurable? Come on, bro. Really? Is this Red's rhetoric?
Hydrogen's next.
Oh, hydrogen. Fusion. Fusion, too. They're calling it fusion, right?
But let's look at some of the typical things that we think of, and we'll work our way back up.
I saw gasoline.
Yeah.
I saw the black goo.
So you've got
TNT,
gunpowder, iron, Teflon plastic. This is the megajoules.
Okay, the megajoules column
per kilogram.
Per kilogram. Okay.
All right, so iron's low. Household waste comes in a little bit higher. So you've got battery, the lithium air rechargeable. This is low. Sodium. So sodium salt actually stores a lot of energy.
I'm not big on sulfur. I'm addicted. Allergic to that. Not addicted.
Peat.
Can't work with the sulfur.
Sodium, coal. Now all of a sudden we're in the 10 to 20 range. Cow dung. And
come on. 15.5.
Yes.
Come
all
on.
these guys that were in the coal mines should have been saving their time and just shoveling cow shit, right?
Yeah, I guess so. Look at that. Oh, man.
Glucose.
Right? Okay. Sugar.
All right. So this is, in our body system, this is a high energy storage system. Sugars, carbohydrates, and proteins. Peat, briquette, wood. So just wood comes in better than coal and cow dung.
Wow.
Right?
Just straight wood. Cut the trees down, dry them, and burn them. Create energy.
PVC plastic. So that plumbing pipe that we've been working with stores a high amount of energy in it.
Wow.
All right. Liquid ammonia.
Oh, that's a bigger one. 18.6.
A little bit higher. Methanol.
Hydrazine?
Here we've got a better form of the coal, the bituminous.
Bituminous coal, huh?
Magnesium's right in this range. Ethanol. All right. So ethanol, we're starting to get up here into the alcohols. And 30.
Okay.
Aluminum a little bit more. There's a lot of energy stored in aluminum.
Ethanol is just a byproduct of, what do we call it? Fermentation, right?
Fermentation.
Of anything. Anything matter, you make ethanol from.
Another type of coal here, then graphite. Now all of a sudden we're getting into the gasoline. This is the E85. That comes in at 33.1.
Of course, 33, huh?
Yeah. Body fat. Look at this.
What?
Look at the way the body stores energy. This is starting to get up there.
Okay.
Crude oil, 41. Biodiesel or vegetable oil, 42. Lithium. So here's what's in a lot of the batteries is energy storage, megajoules per kilogram, 43.1. Here's your regular gasoline, 10% ethanol, 43.51. So gasoline is a little bit better. Just our regular gasoline stores energy a little bit better than lithium. Jet fuel, right, which is kerosene or diesel fuel. 43. Diesel. Look at this. So the diesel that goes in my truck stores more energy than jet fuel does, than gasoline does, than lithium. So diesel's not that bad of an option. Residential heating oil, a little bit more storage. Polyethylene plastic stores 46.3. Polypropylene plastic 46.4. Pure gasoline 46.4. And you got liquid propane gas, natural gas, methane. We're getting up to 55.6. Hydrogen gas. All right. So here's your hydrogen
141.
here. Yeah, 141. So the best material for storing
Hydrogen
energy.
liquid.
Yeah, or gas. It's the same. Look,
It
the
matches.
numbers are
Yeah, I
the
see
same.
that. I see that. Interesting.
The only thing that changes is because it's density, right? The
Yeah, it's
liquid's
density.
more dense.
And probably easier to contain.
But it stores the same amount of energy. So the number one energy storage element material is hydrogen. It just kicks the doors off of everything else. And that's the reason why going forward, we would like to use hydrogen as our storage mechanism of energy because it has the highest specific energy.
It's super abundant. It's everywhere. It's not something that we have to go and like search for. It's in everything. You just have to figure out how to get it out. Right?
Yeah.
Excellent.
These are the things that we'll be considering going forward.
Yeah, no, all great points. Hydrogen obviously is the winner. And how do we make it with the least amount of effort?
Photoelectrolysis, they're saying.
Yeah, well, we're going to see about that. We still might have to do some flywheels, some solar panels, and some flywheel generators.
We might.
All of it. All of it. And we're going to do growing gardens and all this other stuff, and we're going to show everybody, and it'll all be awesome. So we're looking forward to that. It's going to be a great spring, great summer. We're going to see how things go. We're going to try to build forward and try to make our own power. Right?
Absolutely. What else is there to do right now, you know?
Yeah, well, if they're going to talk about shutting the power off, we might as well make our own. Go ahead.
Might as well.
Shut it off. Go ahead. Enjoy it. We'll be back up and powered in no time. So.
All right. Well, I guess that's what I got for tonight, brother.
Great. Thank you very much for the presentation. I thoroughly enjoyed it. And if anybody has any further questions, please leave a comment below. Jason does the comments really well. And if there's anything that you wanted to ask us or talk about that you might know, some other types of technologies, don't be shy. Let us know in the comment section too. We're learning just like you. We're just going through this together, and I really appreciate the flow. I thought it was great. I learned something tonight. So to me, that's a huge win. And I hope you guys did too.
Well, thank you, brother. Yeah, and then Sunday night, right?
To stop the screen share, yeah. I'll try not to have to tell you too many times, but oh, there's you on the screen. Okay, yeah, we got it back to the thumbnail. But yeah, no, thanks a lot. I'll let you have the last words, brother. This is a great presentation. Thank you very much, and I'll play us out.
Yeah, no, it's so I'm in the process now. I've got a new computer where we're going to be getting ready with 2023 graphics. Everything we plan on having upgraded and better and new and fresh, and I'm going to continue the pursuit of these types of energy devices where we can disconnect ourselves from the grid and maybe help some other people do so as well in the same time. So
I do have one update. I'm sorry.
Okay.
So if you don't know already, I'll put the comment below. Our home base is Reality Check. So if they take down all of our channels, we're always going to be posting where we're going to be uploading our content. And we upload our content to Reality Check too. And Sunday at 6 p.m. Central, at 7 p.m. Eastern, we're going to be reading the Gospel of Thomas. So if anybody doesn't know, please tune in on Sunday. And yeah, anyways, you have the last word.
No, that's about it. Thank you for tuning in, everyone. The only place you're going to hear this is beyond flat Earth. Good night, everyone.